interesting papers, assuming that the final author shows up. But we start with the first one, continually learning out of distribution spatiotemporal data for robust energy forecasting. Welcome.
Thank you. Thank you. Hi, hello. Good afternoon, everyone. My name is Aryan Prabowo, and I'm presenting this paper, Continue Learning Out of Distribution Spatial Data for Energy Forecasting. Yeah, let's get started. So let's start with a big question, right? Why are we doing energy use forecasting in the first place? So these data are from Australia, and Australia has an energy market. That means that the price of electricity changes every about like 5 minutes, depending on the supply and demand. If there's lots of supply and then not much demand, the price will go down. If there's lots of demand and not much supply, then the price will go up. So this is how this is the energy landscape in Australia. So therefore, energy use forecasting is important.
Sorry for the interruption.
It's okay. It's okay. All right, we're back. So yeah, so energy use forecasting is important for many different stakeholders in the industry, right? So from the retailer perspective, they need to manage their infrastructure in such a way that they are able to deliver the exact amount of electricity to the right part of the network. For the building managers, some when they manage like big building complexes like this university, for example, some operations are very energy intensive, such as pumping water up a very tall building, and or like changing the water in swimming pool, or like keeping the water warm. So those are like very energy intensive activities, and you want to do those things when the prices are cheap. On the other side of the supply chain, we have the power plants operator who, for example, want to schedule their maintenance only when the demand is low. When the energy is cheap, it's a good time to maintain their infrastructure. When the energy is expensive, you want to sell. You don't want to miss this chance. So unfortunately, to the best of my knowledge, the industry are only using a traditional machine learning model, and sometimes not even that, right? So that is the energy landscape. So that is the landscape at the moment. So, and things can get worse, right? The title of the paper is about out of distribution. Extreme events, for example, COVID-19, changed the energy use distribution pattern, right? So this is the energy use before lockdown. If you see, there are 5 peaks, and then there are 5 high peaks, and then there are 2 low peaks. Those are like the weekend and the weekdays. And after lockdown, things change a lot in this particular building. So there's a huge shift in distribution. If you can see, it started dipping down a little bit just before lockdown because the COVID numbers are already going up, and people are already getting scared, and people are already changing their behaviors. So yeah, this is what the data looks like. This is what the out of distribution looks like. And the way we set up the forecasting and machine learning is we try to forecast the future energy mostly based on the past energy use. In practice, we take the past 24 hours in order to forecast the future 24 hours, right? And the relationship is not necessarily causal. It's only correlational, and the correlation is very complex, right? It's definitely non-linear. Yeah. And what makes things worse is that this complex correlation is already complex in normal situation. When the distribution changed, this correlation also changed, right? That's the issue. That's the challenge that we have at hand. And therefore, what we do is we use this this family of method called continual learning in order to adapt the change due to this due to the change of distribution, right? So they need to learn a new correlation in the new distribution. So what is exactly this continual learning? In traditional offline learning, what we do is we have a huge data set. We divide usually, as usual, into training, validation, and testing. And then we train the model once on the training data set, and that's it. The weights are frozen, the models are frozen, it's never updated again, right? As we can understand, with the setup, the model performance will suffer a lot when they are changing the distribution. Continual learning is a bit different. It is when the models are updated as new data comes in. So yeah, as the new data comes in, the model weights are updated, right? So this way, it is much more adaptive to changes in distribution. So in short, what we do is we use continual learning to perform accurate forecasting even during out of distribution periods. And let's get to the good data set, right? The data set is we take from 4 building complexes, and it's building complexes to protect privacy. What we do is we aggregate nearby buildings into building complexes, and understandably they will have different use, even in the same building complex, they will have different use. And all the data are from Melbourne, Australia. This is a very famous place in Melbourne, Australia, and it's very interesting because this is the city which experienced like one of the longest and the strictest lockdown in the world. I think I don't know if we're still number one. It's not a competition. It's not a competition, but yeah, we are notorious for our lockdown, unfortunately. And so this is what the data set looks like. So the raw data set looks like this, the one on the bottom. If we plot them from 100 to 400, if we plot them for the entire duration of the data set, it will just be a solid blue block. And so I did some smoothing so that we can see the data set. Yeah, as we can see, the data set selection is very diverse. Every single building complexes have very different distribution even before lockdown, right? And I should say the red part are the lockdowns, right? The red parts are the lockdown. Right? Yeah. So this is what the data set looks like. They have it's very diverse. Some are very low use. The others have much higher load. And the other data set that we use is mobility data set. This is already installed by the city of Melbourne, so it's from us. This data set is publicly available, right? And so it does not capture image or videos, so it only counts the pedestrians, so it preserves the privacy. And the best part is that this is publicly available, and so it is useful for other stakeholders such as the energy retailers or power plant operators, right? Building managers can have devices installed in their buildings, so they know what's going on. However, like energy retailers don't have no idea what's going on inside the buildings, right? So this is a very useful data set. And this is what the data set looks like. It's also very varied. And I think, as we can see, even before the lockdown starts, people are already getting very scared 1 week before. So yeah. And in mobility, the impact is even clearer during the lockdown. And so this is just some detail of the data set, because we cannot release it publicly. I try my best to give as much detail as possible, statistical details as possible. I think the interesting thing to point out is that our data set ranges from 1.5 years to 3 years, and the granularity is hourly. So yeah. And this is the setup. As I said before, we use the last 24 hours as input to forecast the next 24 hours. So this is an auto-regressive setup. We have time mobility data. We also have temperature data, as common when we're doing energy forecasting. And we divide our data into two periods, the pre-lockdown and the post-lockdown. So pre-lockdown is everything before this is pre-lockdown, and everything after is post-lockdown. And what we do is in our experiments, we compare 4 different continual learning methods, and they're all implemented with the same deep learning backbone, and that is the and we call it, no, not we call it, it is called the TCN backbone, which stands for Temporal Convolutional Network. And the idea of TCN is it is a very popular convolutional version for when we're dealing with time series, and sometimes it's also known as WaveNet. And so it has 2 distinct features different from the normal convolution you will see in computer vision. The first is dilation, and the second is causal. In dilation, the idea is that you will not move by 1 at every single. You will not shift the window by 1, but you shift by 2. And that means what it means in practice is that when you go down, the receptive field for every single layer grows exponentially, right? So for example, over here, yes, you can see my mouse. Great. So over here, usually this will go to this one, right? This will just go to the bottom, the next tree, but instead this will go to the a further one, and yeah, and so it will skip, it will dilate. That's the idea of dilation convolution. And the other interesting part, it's so the idea is that we need a bigger receptive field. We need a bigger receptive field in this kind of time series data. And the other part is the causal part. So the causal part means that the receptive field is only cover the preceding nodes. So usually in normal convolution, we go to the left, the middle, the left, and the right nodes. But over here, it only goes to the nodes. It only covered the nodes that's happening right now and before, right? So it has no information about the future, because that's the idea of like causality. Yeah, we can only make decision based on the past, not the future. Otherwise, we'll be cheating because we're forecasting the future. Yeah, so this is the idea of TCN, and this is the backbone that we are using, and we're going to use different continual learning methods over this. So over here, what we do is we try 4 different continual learning methods and 2 baseline, and the idea why FSNet and TCN is a bit different is because in FSNet you have to adjust the architecture is a little bit different, right? So it's basically very similar with TCN. And as we can see, the idea is among all the different methods, all the different methods, FSNet is performing best, and most importantly, all the continual learning version is performing way better, lower error than the non-continual learning version, even before lockdown. And the distance, the gap, the improvement is even much more pronounced after lockdown. Yeah. As a comparison of how much of an improvement it is, I put all of the standard deviation there. And so the best performing is FSNet. So what is exactly FSNet, right? So this is the FSNet architecture. The main part is, so if we clear this part out, it's just a normal TCN. What they do is they add these 2 new modules called the memory and the adapter module. So the naive way to do like online continual learning is to update the entire model whenever there's a new gradient descent. It's this one here, right? Right in the middle. So whenever there's a new data, they just update the whole model. The problem is that this is very inefficient, right? And it also risks what is known as catastrophic forgetting. And that means is as you keep on updating the model, as the new data comes in, it will adapt to the new model, but at the same time, it will forget how to perform on the older distribution, on the older task. So that's a issue there with doing it naively. So what do they do instead in FSNet is that they have these two modules. Instead of updating the entire network, what they do is they froze the main backbone, they froze the main convolution, and what they do is they only update the memory module, right? And even then, they don't update the memory module all the time. Not so. What they do is they have the adapter module to decide when to update the memory module. Yeah. So this is very briefly the idea of FSNet. And we also, and since we have the mobility data set, we also do a more analysis on the mobility data. So the idea is we want to compare how much performance gain do we get from mobility compared to what is typically used as contextual data, and that is temperature, and what if they're combined. And the idea is mobility and temperature. They are, and the idea is mobility is about nearly as useful as temperature, right? Which should be surprising because mobility data is rarely used in energy forecasting, whereas temperature is nearly always used. So I think, yeah, so that's our idea so far. And the best part is that these two information, they are disjointed, and that means is when you combine them, you will get improvement from both. So the information contained in mobility are the information not contained in temperature, right? And it's because, and we know that because when we combine them both, we definitely have increased performance. So yeah, we have increased performance before lockdown and after. And going to the conclusion, this is just very quickly, this is our current work with 4 building complexes and 2 periods and 4 methods. Based on this, we launched a more complete benchmark with more buildings, more temporal granularity, and 13 different methods ranging from naive to this continual learning. And if you're interested, please take a picture not of this one, but of this one. Yes, this is the link to this paper, and this is the link to our follow-up work. Thank you very much. I'm wondering if there are any questions.
Thank you so much for your talk. I'm Shadi from Baker Hughes. So my question is, I mean, you showed us results for when we have distribution shift on only energy consumption. What about cases where we have multivariate data and there are different distribution shifts in every single channel? So how could we approach these kind of problems in your opinion?
I think doing exactly this would be a good start. So I think the quick answer is I don't know. I'm not going to say something that I don't know. So I don't know. But I think doing continual learning is definitely a good place to start. And I think if I personally have that problem, I would look at how does this multivariate distribution shift? Is it just one variable? Is it like all variable? How about the covariates, the correlation metrics? Is it also shifting and whatnot? Yeah. So yeah, definitely that's a very interesting problem.
Not a question. I'm a supervisor of this project. So we have another paper where we have a memory network where, you know, when you can have memory that is shared across different channels of information. It's AAAI last year. I'll share.
Thank you for your presentation. In the beginning of your presentation, you said that one of the possible applications was electricity price forecasting. For that, you would probably need to expand this to an electricity grid-wide approach. Would that be feasible with this method, do you think?
Sorry, I missed your question. What
would-
approach?
Would your method work to apply it on a electricity grid-wide context?
Oh, yeah. I think it's actually the other way around. If you look at the literature, most of the energy forecasting literature is on the big aggregated energy. And I'm not sure, but my instinct says that it might be actually easier because all of let's go to the data, right? Because this is the mobility, the energy data is on top, yeah. Because all of this different noise will cancel out each other when you aggregate them. So it is actually, I would say it is actually harder when you do on building level, yeah. And so yeah, I think that definitely that's true. Once we do building, if we're doing better at building level, it will actually help us when we aggregate them for the prices, yeah. Thank you.
And the second paper of the session will be pre-training contextual location embeddings in personal trajectories via efficient hierarchical location representations.